Okay, I'm just going to do a quick recap of the most difficult concepts from what you should have watched this week in the lecture videos. They're more explained in there. But I'm going to start with molecular geometry. Molecular geometry is based on our electron domain geometry, but it's really like what you see when you have valence electrons on your central atom. So if you have dots on your central atom, it's going to change the shape. Okay, so what I'm going to do is I'm actually really just going to look at this page. If you printed the previous version of the notes, I would reprint this specific page or come pick up a packet in the office. These are all of the shapes at all that you have to know for Vesper theory. Okay, I really like this chart because it goes through, if you have no lone pairs on the central atom, this is like the electron domain geometry for everything. Okay, these are your only options, and we talked about those together last week. Now, if you start switching out one of those domains for dots, you start changing the shape. So you have bent with 120s here. You have trigonal pyramidal, and then bent with 109.5 here, or really like 104.5. Here you have take 1 is seesaw, 2 is T-shaped, 3 is linear. And then octahedral, if you take 1, it's square pyramidal, 2, it's square planar, 3 is T-shaped, and 4 lone pairs is linear. Okay, these are all the shapes you should possibly have to know. I highly recommend doing like a Quizlet or something with these because you have to be able to count the domains and then use the number of which ones are lone pairs to figure out the shape. So if it doesn't like come easily to you, like imagining what it looks like in your head, I would make a Quizlet or note cards or something to review these, okay? Because I'm not giving you this chart. So you have to be able to figure out the shape without this chart. Okay, so this is kind of the most important thing about Vesper theory. And then here, this was practice. And then that the angles aren't exactly 109.5 if you have like dots on there, but as long as you know 109.5 for tetrahedral, you're fine. Let's see, that was practice. And then what happens if you have multiple central atoms? You just look at each one individually. This has 4 domains, tetrahedral. This has 4 domains, it's also tetrahedral. But this one's bent for molecular geometry. Notice not all Lewis dot structures are drawn with the correct orientation. They do not have to be drawn correctly in 3 dimensions. So keep that in mind when you're determining your electron and molecular geometry. And so this one, you're supposed to find those. Polarity in general. So this is if you have electronegative, right? We did this together. But if you have different shapes, you might have an overall polar molecule or an overall non-polar molecule. The rule is if the vectors add up to 0 or if they cancel each other out perfectly, it is non-polar overall. So like these two are the same size, exact opposite direction, non-polar overall. These two are both kind of pointing up. Like if I were to smush them together, I would have an arrow going up. So that one is polar overall. You do get a molecular dipole. If you want to actually add vectors, which you would learn in physics, if you add this one and this one together, you essentially make a parallelogram. The added vector looks like this. It's longer, but it's in the middle direction. You can kind of figure it out without learning how to do this exactly. Okay, exact opposite, non-polar. If there are, the rule ends up being, for the most part, okay, if it's completely symmetrical, so like if all the things added on the outside are all the same element, like all hydrogens or all chlorines or whatever, and there's no dots on the middle, no lone pairs on the middle, it's going to be non-polar. Okay, everything's going to cancel out. If there are dots on the middle, it's probably not going to cancel out. But if you think about tetrahedral, for example, that has 1 lone pair, so that's a trigonal pyramidal, right? It's like standing up. So those are all going to go up a little bit and they're not going to cancel out. Whereas a trigonal planar one, like this example right here, is going to cancel out because they're all on the same plane. So they're going to cancel each other out. So trigonal pyramidal is always going to be polar, whereas trigonal planar is not. Okay. I'm happy to help with polarity if you guys need it. So most of the time dots on the middle mean it's going to be polar. The only time they would cancel out is if it is square planar. So I'm going back to my shapes here. This is the only time that if you had dots on the middle, if all these things were the same, they actually would cancel out. Otherwise, if you've got dots on the middle somewhere, it's probably polar. Okay. Let's see. So that was polarity. And then valence bond theory. Okay, so I'm just going to talk about the important thing really about here. It's that bonds overlap, okay, or that the orbitals overlap to make a bond. And what you need to know is all, I'm going to skip over all of this, is right here. If you can count domains, you can tell me what the hybridization is. If it has 2 electron domains, it is sp. If it has 3, we added a p orbital, so it's sp2. If it is 4, we added a p orbital, so it's sp3. If you have 5 domains, p doesn't have any more orbitals, it only has 3. So we added a d, so it's sp3d. And if you have 6 domains, it is sp3d2. So as long as you can tell me the number of domains, which you need to be able to do for Vesper anyway, these always match up. So this is really all you need to know. Okay. Now going down here, multiple bonds, a single bond is a sigma. A double bond has a sigma and a pi. Anytime you start adding a double or a triple bond, we're adding pi, which is just what that type of bond is called. It's above or below, or above and below, really, that central bond. So anytime you have a double bond, it is a sigma bond and a pi bond. And then MO theory. Okay, so really the only thing you need to know about MO theory, you do need to know paramagnetism versus diamagnetism. If you have unpaired electrons or not is going to affect their magnetism. And you don't have to actually make these new diagrams, all right? So you will be given these. Okay? These are your 2 options for molecular orbital diagrams, and I will give you whatever one it's supposed to be. If you printed the old worksheet, you might want to print the new worksheet or get it from the office for the module 10 worksheet. We're just going to focus on valence electrons, okay? So you'll count the valence electrons, and then you just fill them up from bottom to top in the way that these are. That's literally all you do. You don't have to draw these. I will give you the thing. So you'd be like, okay, oxygen has 6 valence electrons. So if I had 2, that's 12. So I fill from the bottom up. So I go 2, 4, 6, spread out before you pair up, but I can do that 8, 10, and then I have 2 more. So spread those out before you pair them up. So this is what it looks like. Ignore this one over here. So I do have 2 unpaired electrons. So that would tell me that this can be paramagnetic. Okay. These are the ones that they look like for, in reality, for all the ones you could possibly see. I'm not going to give you anything more complicated than these, because once you get past sigma to pi antibonding, it gets really messy. Okay. So this is really like high-level chemistry explaining wise, but if you can fill the orbitals, you can do it. The last part of this is determining bond order. Where's the bond order? Oh, bond order. Where did it go? Hang on. Sorry, I had to go back. Bond order is the number of bonding minus the number of antibonding divided by 2. So bonding is when they don't have the star. Antibonding is when they do have the star. So like I'm going to do that one here that I was talking about before. So I have bonding wise, I have 2, 4, 6, 8. Antibonding, I have, so antibonding is the stars, right? I have 1, 2, and then down here I have 3, 4. So you would do 8 minus 4 is 4, divided by 2 is 2. So bond order is 2. And remember, we have talked about bond order before. Bond order of 2 means it has a double bond, which would be stronger than a single bond or weaker than a triple bond. Okay, that's it. You can do the worksheet. You will be good. So I will go over the worksheet on Monday. Hopefully that will help out. That was hybridization, Vesper. I think that's everything. So if you need me to go over anything else, I'm happy to do it on Monday. I did print off stuff if you want to come get it from upstairs in ICN 2000 suite. Emily has them at the front. Otherwise, shoot me an email and I'll see you guys on Monday.